Hi, my name is Boyana Martinova, and I'm a graduating senior in the math department. And I just wanted to talk a little bit about some of my previous research coding for the math software Macaulay 2 under the advisement of Dr. Carl Schweed. So the goal for our previous project was to improve the functionality of this math software Macaulay 2, which focuses on computations in algebraic geometry. And we were hoping to add some new methods and optimize some of the existing ones. Together with a few other students, we were able to create the package FastLinAlg, which focused on some key applications in linear algebra. The main ones being we provided a method that finds the submatrix of a given rank in a provided matrix if it exists, another method that determines if a variety is regular in a given codimension, and the method that I'll be talking about today recursively computes the ideal of minors in a matrix. So essentially it's returning the ideal of submatrices of a given size in an input matrix. And this was targeted at matrices where the entries are polynomials in many variables, typically also with a high degree. So actually, Macaulay 2 has a method that computes these minors, but the current implementation is pretty slow and it's not really optimized because the default evaluates the determinants using what's called the various algorithm, which is pretty efficient when the polynomials have a low degree or they're not in that many variables, but it's really slow otherwise. And the current implementation does allow the user to use a cofactor expansion, but again, it's not optimized and it performs some unnecessary calculations. Now, when we're thinking about a polynomial that has, a high degree with a lot of variables in it, and we're considering, multiplying a lot of these polynomials together, that within itself, that computation time is going to be very slow. So when we're performing a lot of these unnecessary calculations, we can expect that the existing cofactor expansion method is going to be a lot slower than it needs to be. So what we wanted to do is target a couple of key improvements that would hopefully lead to an improvement in the computation time. The first one being we wanted to recursively find determinants using cofactor expansion. And with that, we wanted to eliminate all of these unnecessary computations that we were seeing in Macaulay 2's existing method. And we also wanted to multi-thread all of this so that independent computations can kind of be going on at the same time. So let's talk a little bit about what it means to recursively find determinants, specifically, using this cofactor expansion. So let's say we wanted to find the determinant of a matrix. The way that we would do that is we'd choose either a row or column, and we'd go across the entries in that row or column, and we'd multiply each entry by the determinant of the submatrix that's formed when we exclude the row and the column that entry is a part of. So let's look at this graphic to the left, right? And if we're trying to find the determinant of this matrix A, and let's say we choose the first row, we would take A11 and we'd multiply that by the submatrix here, by the determinant of the submatrix here in green. We'd subtract that by A12 multiplied by the determinant of the red submatrix, and so on. So what our method does is it first computes and stores the 2 by 2 determinants, and then it recursively builds upon that. But the key here is that we're only computing the determinants that we need for the next step in the recursion. So again, in this graphic, instead of computing all of the 3 by 3 determinants, we would only be computing the 4 that are outlined here. So let's think about some results and the time speedups that this actually led to. Consider, let's say we're trying to find 4 by 4 minors in a 6 by 6 matrix with degree 1 entries, but we're varying the number of variables that in each matrix entry. So we found that with more complex matrices, our method was leading to large time speedups. Notably, let's say we're looking at a matrix with 10 variables per entry, which is what we're looking at here on the right side of this graph. Our implementation found the ideal of 4 by 4 minors approximately 54 times faster than Macaulay 2's default implementation using this various algorithm. And compared to Macaulay 2's cofactor expansion, again, we're going to expect that Macaulay 2's cofactor expansion is faster than its various algorithm, but since it's still doing all of these unnecessary computations, we were finding that our implementation using the cofactor expansion was still at least twice as fast when each entry had more than 2 variables, and that number was just growing as the number of variables increased. So yeah, I guess that's just a quick introduction to some of the work that we were doing for Macaulay 2, hoping to improve the software. So thanks so much.